Okay, good afternoon. There were 10 minutes in the afternoon. Okay, let's wrap up diodes today and then we'll introduce BJTs, transistors. So, let's bring up. How many of you have lab on Monday? Mondays, does anyone have 361? And you're doing lab 3? Oh, because last Tuesday was a Monday schedule. Okay. So those of you who have Monday labs, it's just I I just don't like it because it's very early in the week. We barely get a chance to delve into a topic. Ideally, I would say we do lectures Monday, Tuesday, Wednesday, and then do labs on Thursdays and Fridays. But it is what it is. Um, but I did want to address that the lab write-up runs about 2.5 pages. Okay, lab 3. And then most labs, it's like between 2 and 3 pages. The way those write-ups are written is as a study guide. Okay, so there's only just enough technical jargon in there with equations that will allow students to read through it and solve the pre-lab. So please ensure that you are reading the lab write-ups. Do not just skip over them. They are very well written. I don't claim any credit for them. They were written a long time ago. The minor changes are made over the years, but they are very well written. So please, every time you are doing the lab, always read the lab write-up. And there are equations given along with the lab write-ups that will allow you to actually do it. So they are not written like a textbook, like a technical textbook. They're written more as a study guide. And you can, as soon as you read it, you can realize the difference in the tone. Okay. The reason why they're written like that is just because the way the structure of the labs and the lectures are. So anyway, having said that, let's get to our class notebook. So we stopped here, the Zener regulator. There are a few more wave shaping circuits we need to look at. And the first one is the diode clipper. Okay, so clipper is so called because it clips part of your AC waveform. So far we have looked at circuits where it's either DC or just AC applied to it, right? Now we're looking at circuits where we have both AC and DC waveforms being applied. So this is the first circuit where we see both working in conjunction. Okay, so here's a source. V in of t is a AC input. It's a sinusoidal waveform. This is your input waveform. And this is my acronym for input, I/P, and O/P would be output. So actually, this would be input, and this would be the output. If you use the ideal diode model to analyze this circuit, which is what I always prefer, I can redraw my circuit like this. So this is diode A and diode B. So I'm going to call it DA and DB. In the positive half cycle, diode DA would be forward bias and diode DB would be reverse bias. And so I would say diode DA is on and DB is off. And the exact opposite happens in the negative half cycle. In the negative half cycle, diode DA is off and DB is on. So again, ideal diode model is a very straightforward and, dare I say, easy method to quickly analyze circuits. Okay, so if that's the case, I can simply model my circuits like this. Actually, because I'm taking only positive half cycles, Let's do it this way. And I'm going to ignore the 6-volt and the 9-volt battery for now. Okay. So I have this as a short circuit. And this will be an open. What is my V out? V out is taken across those two terminals where the diode is connected. So V out goes to 0 because now voltage or current simply has a pathway through the diode. Same thing happens in the negative half cycle. The other diode is forward bias, so the circuit looks like this. A is off, B is a short circuit. The result is VO is 0 volts. Current simply has a pathway in this direction. So in both cases, the waveform is simply flipped. Output is 0. Let's take a pause while you think over this and let me know if you have any questions. Does that make sense? So far, so good. So now let's look at our circuit where you have inserted a 6-volt battery and a 9-volt battery in series with the diode. What does it mean? If you insert a battery in there, all it means is whichever terminal the battery is connected to is held at that potential. So in the case of diode DA, we have connected the positive end of the 6 volts to the cathode. So that means the cathode of diode DA is held at plus 6 volts. If the anode is at 0 volts, is diode DA on or off? It's off. I should not have agreed that quickly. I should have waited to see who would say on. Anyway, so as long as the cathode is higher than the anode, the diode remains off, right? It's fundamental. Now, irrespective of what voltage the cathode is held here, the anode is connected to the negative. So diode DB is going to remain off. Okay. So in the positive half cycle, now this is with the batteries connected. Okay. So with batteries, and I should have stated here without batteries. Okay. With and without batteries. Let's make it more clearer. Okay, so this is without batteries, and this is now with batteries. So regardless of what battery is connected to diode DB, DB is always going to be off in the positive half cycle, right? Because it's flipped. The anode is now connected to the negative end. So diode DB is going to be off regardless of what happens. But what happens with diode DA? Diode DA remains off until the anode or the voltage of the anode is higher than 6 volts. So look at the positive half cycle right here. We are applying plus 15 volts and minus 15 volts. Okay, so 30 volts peak to peak, 15 volts peak. Oh, actually, yeah, this is not marked, but let's say this is minus 15 right here. Okay, plus 15 and minus 15. So in the positive half cycle, DB is off. DA remains off until the anode goes 6 volts higher than the cathode. So until 6 volts is crossed, diode DA is off. at this level. Does that make sense to everyone? Diode DA remains off until the V in voltage exceeds 6 volts. When it crosses 6 volts, diode DA turns on, it becomes a short circuit, and then V out goes to 0. So until DA is on, V out equals V in. And hence V out follows the exact same path as the sinusoidal waveform. Once DA turns on, output is now V out is equal to 0. Output waveform stays at 6 volts. When it drops below 6, diode DA turns off again, and then V out again follows V in, or the shape of V in. And hence we get a waveform that looks like this in the positive half cycle. So this is V out. And this is at 6 volts. So the portion of the 15-volt positive supply that was coming is now clipped, hence a clipper. Let's take a pause. Let me know if you have questions. Yes. Plus 15 and minus 15 right here. So 15 sine omega t, V of t is Vm or Vp sine omega t. And Vp is only half of peak to peak. So plus 15 and minus 15. Yes. Good question. So the question being asked is what happens if we flip the 6-volt battery? So what happens then? It's always on because cathode is held at a negative voltage. So diode will always remain on. Because even if the voltage goes to 0, diode is going to remain on. The only time diode goes off is in the negative half cycle when the anode will fall below 6, below 6 volts, right? So it's more positive with respect to the cathode. Yes. No, it's not modeling the Zener diode. No, it's simply a diode in forward and reverse bias. Yeah. I saw another hand somewhere to my right. Okay. So yes, there are multiple versions of clippers where the batteries can be connected in positive direction or the negative direction. And we can, depending on our requirements, we can change. But the same thing happens in the negative half cycle. In the negative half cycle, DA is always off, but DB is now connected to a 9-volt battery. So in negative half cycle, DB is off until V in exceeds 9 volts, or actually I should say exceeds minus 9 volts. V in goes less than minus 9 volts. And until that happens, output follows input. And so we obtain V out as a clipped form of the input voltage V in. Make sense? Okay. All right, then let's look at another clipper circuit, but this time we use Zener diode clippers. The obvious downside of using regular diodes as clippers is that we need a battery or a DC voltage source. Okay. So if we use a Zener diode, we don't need to use a battery. We can simply use it in reverse bias, and that gets the job done. So if you look at this branch right here, we have a regular silicon diode D1, and we have a Zener diode of 9.4 volts connected in reverse bias. And then we have 3 regular silicon diodes, D3, D4, and D5. So I'm referring to circuit in figure A. The question being asked is determine the output. Okay. So for circuit A, what is VO? Let's look at D3, D4, and D5. What do we see? They're all connected in series. And if we say they're regular silicon diodes, let's assume VD is 0.6 volts. 0.6 volts. So first thing is that the branch on the left would affect the positive half cycle. And the branch on the right affects the negative cycle. Right? Because the anode is connected to the negative, and on the left, the anode is connected to the positive. So the left branch affects the positive cycle, and the right branch affects the negative cycle. So the combined voltage drop, VD3 plus VD4 plus VD5, means the diodes are going to remain off in the negative cycle until Vin drops below 1.8 or minus 1.8. In the positive cycle, actually, let's finish negative first, then I'll talk about positive. So in the negative cycle, D1 and the Zener is off. We won't worry about that for now. We just leave it as it is. And the combined voltage drop, VD total, is 1.8 volts. So V out is equal to V in until V in is less than minus 1.8 volts. Minus means simply in the negative half cycle. That's all. The path follows a similar structure to the previous example. Yes. So I was assuming that the individual single diode voltage drop is 0.6 volts. So 3 diodes together would give us 1.8. If you assume 0.7, you would get 2.1. If it's given, we simply take that. If it's not, you assume whatever you wish. Right? You make an assumption. I assume 0.6 volts diode drop and just, run with it. So let's take a pause before I get to the positive half cycle. Okay. All right, let's look at the positive half cycle. What happens there? We have the Zener diode that is connected in series with a regular diode, D1. Voltage for that Zener diode is 9.4. voltage for diode D1, let's assume 0.6. So VD1 is 0.6 volts and VD2 is 9.4 volts. Now the key thing here is that the Zener must be connected in reverse bias. But we would still take the voltage drop in this direction. Remember, diode voltage for a Zener diode would be minus, but if you simply say Zener, then the positive is always cathode, negative would be at the anode. So it'd be plus 9.4. You simply add them in series, you get 9.4 plus 10. The Zener diode is not going to turn on until the anode is 9.4 volts below the cathode. Again, Zener diode is rated for a certain voltage. Zener diode is rated for a certain voltage. It is operated in reverse bias, meaning it does not turn on until the anode exceeds, sorry, not exceeds, until the cathode exceeds the anode by its rated voltage. So if VZ, for example, is rated for 5 volts, then for the Zener diode to turn on, the cathode must be 5 volts higher than the anode because it's used in reverse bias. Remember the voltage regulator that we just did last class? It's always operate in reverse bias, reverse breakdown, third quadrant, meaning the anode must be higher than the cathode. Sorry, the cathode must be higher than the anode by VZ. And so plus at the top where the cathode is connected, minus at the bottom, that gives me a VD total of 10 volts. The diodes are not going to turn on. D1 and D2 are off until Vin is greater than or equal to 10 volts. Once it exceeds 10 volts, diode D1 turns on because it's forward bias. It drops 0.6 volts. The remaining 9.4 volts is dropped across the Zener. Zener is rated for 9.4 volts. Now the cathode of the Zener is higher than the anode by 9.4. So that also turns on, provides a short circuit. V out goes to 0, and the waveform is clipped. Yes. So, well, as a student, it would be given in the problem statement. If I was simply analyzing as an engineer, my first go-to option is always the ideal diode model. So the question being asked is, how would we know which model to use? So again, as a student, what model to use would be stated in the, would be given in the problem statement. If it's not given, feel free to assume anything you want. But as a working engineer, you're free to choose whichever you want. And ideal diode model is always my go-to model of choice. So anytime I analyze a circuit, I would always use an ideal diode model because it's far easier to analyze. Short circuit or open circuit, and that's it. And then once you analyze the circuit based on that, then we can go in and use a different model to determine our exact voltages and currents. Even with just using an ideal diode model, and we neglect the effect of like 0.6 volts, the diode voltage drop, the results are surprisingly accurate. We don't do it in this class, but in the other semiconductor class that I'm teaching for EE majors, we analyze the same circuit with 4 different methods. One of the methods is ideal diode. Another one is iterative analysis. The third one is load line method, which we will do in this class. And there's a 4th method. So we analyze using all 4 methods, and the currents and the voltages are pretty similar. The ideal diode voltages are, of course, far from the normal ones, but the current is actually pretty within range. Yes. No, because it's off, So the question being asked is what happens in the positive half cycle? In the positive half cycle, all the diodes are off. Let's take the right branch first. So in the positive half cycle, D3, D4, and D5 are always going to remain off. No change, right? But D1 and D2 will also remain off until Vin exceeds 10 volts. So as long as Vin is below 10 volts, let's say we use the same thing as the previous one. This is Vin. And let's say this is plus 15. So regardless of the voltage level, D3, D4, and D5 are off because their anode is always connected to the negative end, right? Now, the left branch, D1 and D2, voltage is increasing from 0, 1, 2, 3, 4, 5, 6. That is far below 10 volts. So diodes D1 and D2 are also off. If they are both off, what is V out? This is off, this is off. It may as well not be connected. The only circuit, the only component in the circuit is that resistor. So V out is equal to V in, barring a simple voltage drop or something, right? So V out would be approximately equal to V in. So V out would follow this shape right there, because there's no other pathway for the current to go through. Now, once V in exceeds 10 volts, let's say this is 10 volts, diodes D1 and D2 are both on, and because they are both on, it's a short circuit. So now current has a path to flow through the diode. So it now goes from here to here, this direction, and V out goes to 0 volts. Actually, not 0 volts. It's going to get clipped, right? So it's going to stay at that voltage. You had a question, Jackson? Somebody, okay. And so it gets clipped right here, as long as it stays above. This current now has a path to go through. Once it falls below 0, that's when it turns off again, and then requires 10. The Zener diode and the diode drop holds the voltage at 10 volts. Right? The job that was done by the battery in the previous circuit is now done by the Zener diode. In the previous circuit, we had a battery of 6 volts. So if the diode becomes a short, the battery voltage is available at the output. Hence, we get a flat line of 6 volts. I think I skipped over the step so I could see the confusion. The faces. So the battery is connected directly to the output, and that's the 6 volts we are measuring. And the same function of the battery is now done by the Zener diode. The Zener diode drops 9.4 volts across it. The diode, silicon diode, drops 0.6 volts across it. So 10 volts is maintained across the output. The current is still flowing through that pathway, but the voltage is held at 10 volts. Hence, there is no need of a battery. Okay, no need for the battery. But once it falls below 10, then again, diodes turn off. V out again is equal to V in. Yes. At which point? So this is V out. Here, no, it's not. It's not 0. I was talking with ideal diodes. If it's ideal diode, then it goes to 0. But we have a 0.6 volt in the forward bias and then 9.4 in the Zener. So that was incorrect on my part. All right, let's take a pause and let me know if you have questions. Yes. So the negative half cycle. Okay, sure. So the negative half cycle, this entire branch on the left, D1 and D2 are going to be off. right? Because the anode's connected to the negative. So the Zener diode doesn't really matter because diode D1 is going to be off. Does everybody see that? The Zener diode works in reverse bias, but it's connected in series with D1. D1 is for the entire negative half cycle, D1 is going to remain off. Okay. So for the negative cycle, D1 is off. So the voltage level of the Zener diode does not matter. So the left branch is irrelevant. On the right side, the circuit would look like this. We have positive here, negative here, and we have these three diodes. Each of these diodes is now forward biased because the anode is connected to the positive. So all three diodes, D3, D4, D5, are forward biased and are on. And it takes them 0.6 volts to turn on. So if it takes them 1.8 volts to turn on, it's going to hold the output at 1.8 volts. And hence, your negative half cycle is going to look like this. So let's say we are applying 15 volts. Output is like this, minus 1.8 volts. And this is minus 15 volts. Does that make sense? So almost the entirety of the half cycle is clipped. Yes. It would just be 0. Yeah, if it's ideal diodes, it would just be 0. And the application of this kind of a clipper circuit is in surge protectors. So you put a Zener diode in there, your voltage exceeds a positive or a negative, you put two Zener diodes back to back in parallel, sorry, not back to back, in parallel circuits. If voltage exceeds in either direction, the Zener is gonna sink more current through itself and keep the output voltage constant. So if you have a Zener diode of 120, 130 volts, positive direction, one in the positive direction, one in the negative direction, in parallel, surge protectors would have two of them. Yes. Exactly. So the statement being made or the question being asked is the limit of that surge protector would be the power handling capability of the Zener diode, and the answer is yes. Yep. There's another hand I saw here. Any question? So what's the downside of this circuit, of the Zener circuit? Downside of Zener clippers versus the previous one. With a DC battery, you can change the voltage level. With a Zener, you're fixed. So you can't change the voltage level. Okay. Wow, 44. All right, diode clamper circuits. So let's go through this one a bit more quicker. So I'll explain in very quick and general terms what happens. You have this diode right here in the positive half and the positive direction. Ignore the battery for now. Let's say you simply have a capacitor. You have a capacitor and you have a diode like this, and it's connected to an output load resistor, right? V out. What happens in the positive half cycle to the diode? Positive half cycle circuit looks like this. Diode is a short circuit, right? V out is equal to 0. What happens to the capacitor? EE201, chapter 3. It charges. plus minus. Current is flowing from left to right. Passive component, passive sign configuration. If it's flowing from left to right, point of entry is always plus, point of exit is minus. Capacitor charges with plus on the left, minus on the right. Now, negative half cycle, what happens? Flipped, diode is off. Capacitor is now fully charged, but there is not a big pathway for the capacitor to discharge. What do we see? We have a fully charged capacitor. It's in series with a battery, or at least in series with whatever V in is. It's in series, so it looks like this. It adds up. And so now your V out is equal to VC plus V in. So a capacitor, let's say it's whatever value of the capacitor you have, will start to discharge in the opposite direction, meaning it has stored energy. The stored energy is now in series with the incoming V in, and all of that is sent to the output. So your output is now VC plus V in. And so whatever V in value you have, capacitor is like a DC, right? It's fully charged, it's DC. It cannot discharge very quickly. And so whatever V in you apply at the input side is now going to be clamped at a certain DC level that is provided by the capacitor voltage, VC. So now you have attached a DC component to your AC signal. So what happens here in this circuit is that the capacitor charges with plus on the left, minus on the right. In the negative half cycle, diode turns off and the entire waveform is shifted down, because it now has a negative 10-volt level. So the reason it's negative is not negative, but the reason it's 10 volts is because we are applying a 5-volt battery in series with a diode. But simple clamper circuit, you have a capacitor, you have a diode. One half cycle, the capacitor charges. The next half cycle, diode turns off. So the entire capacitor voltage is now available at the output. And that's the basic operating principle. In this circuit, we are connecting a battery in series with our diode. So the cathode is always held at minus 5 volts. And because the cathode is always held at minus 5 volts, that voltage is now available at the output. Capacitor charges from V in, and then the battery is also connected at the output. So there is no clipping of the input waveform. Okay, there is no clipping of the input waveform. The entire input waveform is available at the output. It's only the ground level of the waveform that is shifted from 0 either to a positive level or to a negative level. So depending on where and how you connect your diode, if you flip the diode, meaning the anode and the cathode terminals are flipped, then it'll be a positive level. In this circuit, we have a negative clamper. If you flip the diode, you'd have a positive clamper. Okay. I have about 10 minutes left and I want to start chapter 3. So I'm going to move on from here. If you have questions, I'd be happy to answer them after class. So this is the end of chapter 1, diodes. We'll begin BJTs, transistors. Bipolar junction transistors. As I stated earlier when we began diodes, the reason we call it bipolar is because the current flow that results in these devices is due to the flow of electrons and holes, both charges, positive as well as negative. Okay, hence it is known as bipolar. So even diodes technically are bipolar devices. Okay, and then of course it's a junction. A diode is a single junction device, so diodes are always labeled as 1N, 1N 4001. Okay, transistors are two junction devices, and so they are always labeled as 2N. So any transistor you buy on the market will have a number beginning with 2N. So I believe I talked about this a little bit early on in the quarter, so I'm not going to rehash the same stuff again. The transistor was the first solid state device that was that was created. First invention, prototype was presented in 1947. It was a point contact transistor. And the point contact simply meant you had a germanium crystal. It had a semiconductor that was attached to a voltage source. There was a gold wire running right down to the tip. And then when it made contact in there, they could see a rectifying and an amplifying effect of the current that was passing through. Okay. It consists of two PN junctions. So it's two back-to-back PN junctions. If you have PNP connected together, you have a PNP BJT, or you have two back-to-back NP junctions, then it's NPN transistors. NPN transistors, for various reasons, we'll go into some of them, but not all in very detail, are the most popular ones. So NPN transistors are more popular than PNP transistors. Okay, for a similar size, similar design, similar cost, NPN are always preferred over PNP. There are many circuit configurations where we use both NPN and PNP together. Okay, but if you're just using like discrete transistors or for discrete circuits, almost always prefer NPN transistors. The three terminals are labeled as collector, base, and the emitter. Okay, so the C stands for collector, base, and emitter. The transistor symbol, as you can see here, is typically drawn like this. You have one line, one vertical line. You have two lines at an angle. This is always known as the base, B. And the emitter is marked with an arrow, either an arrow pointing out or an arrow pointing in. And that arrow indicates it's the emitter. And obviously the third terminal is the collector. So if you see here in this symbol, arrow is coming out, so it indicates an NPN transistor. And an arrow going in is a PNP transistor. Okay. Voltages and currents are measured, well, voltages are measured between two terminals. So we could say VBC, VBE, VCE. Voltage is measured between any 2 points. So the voltages for a transistor would be VBE, VBC, VCE, and so on and so forth. Okay. Currents are directly referred to with their terminals. So IC, IB, and IE, collector current, base current, emitter current. Just a slice of an actual BJT transistor. This is by far the most common packaging of a transistor. This is sliced in half. You would see this epoxy material, like, there'll be a small component in your lab kit with black epoxy packaging with 3 terminals coming out of it. It's about this small in size. Okay, this is highly enlarged. And this is the actual transistor in there. This is not even the actual transistor. The actual transistor is just this. That's it. Think That's your aluminum pad. And it's large just to make contact. The actual transistor is right here. That's small. Okay. And the rest of this is just packaging. And so you can see that in your lab kits. There'll be a device, or at least 2 of them in there. Okay. View from 30,000 feet. I can talk about this next class. NPN transistor. Now, it would be very easy to just say, okay, these are 2 back-to-back PN junction diodes, right? But that's not why it's interesting. The reason is the physical construction is very different than just 2 normal PN junction diodes. Okay. Whatever we discuss applies to both NPN and PNP. Okay. The only thing is electrons are switched for holes in both. That's the only difference. And hence the current flow is in the opposite direction. But the explanation applies to both kinds of transistors. For the most part, we'll just stick with NPN. So here you have an NPN transistor, right? The collector is by far the biggest physically. Okay. It's by far the biggest. Okay. It has some amount of doping. Then there is the base. The base is by far the thinnest or the smallest of these regions. Okay. So the base, which is right here, is the thinnest. And the emitter is the smallest. And it's the most heavily doped. The most heavily doped material of the 3. Okay. And hence the name emitter, because it emits a large number of free charge carriers. Free means able to move, right? So the emitter is the thinnest. I mean, the emitter is the most heavily doped. The base is the thinnest. Collector is physically the largest in size with a doping somewhere in between. Okay. As the name suggests, emitter will emit the charge carriers and the collector will collect them. Okay. So the base and emitter junction, EB or the BE junction, behaves like a true diode, meaning you apply a forward bias to it, charge carriers are free to move. In response to that applied voltage, current flows in the direction of the anode to cathode. Okay. Then they go into the base. The base, being very thin, cannot handle all of the free charge carriers that have arrived. Okay. And so what happens is, instead of the electrons coming into the base and recombining with holes, the sheer number of the free charge carriers arriving into the base cross over into the collector. And there's a few other illustrations, but I just wanted to cover at least this portion. It's basically the emitter base junction behaves like a true diode. So you forward bias the base emitter junction. So the base emitter junction is forward bias, which is right here. You apply a positive voltage to the base, negative to the emitter. Forward bias. So a large number of electrons in the entire material cross over into the base. But because the base is very thin and is the most lightly doped of the 3, there are not enough holes available in the p-type material to recombine with the electrons. So many of the electrons are like, what do we do now? Well, then we apply a positive voltage at the collector and the negative with respect to negative at the emitter. And so when we do that, the electrons, some of them recombine with the base, but the majority of them cross over into the collector, attracted by the positive charge of the external supply voltage. And so it does not behave like a true PN junction diode. The second, the collector-based junction, I mean. It does not behave like a regular PN junction diode. So there's a current flow that results through the collector. So some of it goes to the base, but most of it would go to the collector. And that gives us a amplifying effect. A small input current at the base results in a very large current at the output at the collector. And so we'll study that as we go along later on in this chapter. And having covered this, we'll just stop right here, and I will see you all on Monday. Monday quiz, again, general announcement based on Monday, Wednesday, Friday of this week, right? It will not include BJTs. Okay, it will not include BJTs, but clipper clampers are fair game. Okay. So yeah, there is a homework. Can't recall what the deadline is. But again, check the due dates on Canvas. I will update it later today, and I'll also post an announcement. And I'll post an announcement of the Monday quiz also later tonight. But again, just in general, everybody should be aware by now that every Monday we'll have an in-class quiz. Okay. All right. Have a good weekend, and I will see you all on Monday.